Hey everybody, it's Ripley back again. Oh boy. Okay, this is going to get a little bit interesting because if you recall from the very last section, remember how things got into trouble here when we started defining this area and all of a sudden we lost our function. We sort of lost our ability to split this thing nicely up into functions of x. If you recall, that was one of the really powerful things both about parametrics and about polar coordinates. Remember polars? Now, you don't have to be too afraid because I promise the polars aren't going to get out of hand. You don't have to remember the difference between a limaçon and a limescate. You can always look it up. But you do have to remember a couple of things. The most important things that you have to remember about polars is that x equals r cos theta, y equals r sine theta, what was it, x squared plus y squared equals r squared, and then tan theta equals y over x. All right. Now, really, we don't use this thing at all in this guy. All right. Now, I'm gonna tell you something really quickly. I'm gonna give you some information, which is gonna sound a little bit hoopty, but just bear with me and understand that the whole reason that we're doing this is so that we can get ourselves out of trouble if we can't define that base region in XY. Remember, if I've got some goofy region here, right, that I'm defining, and this guy's our D. Remember when I take my integral over that guy. All right, so we're gonna start defining these a little bit differently, and I'm gonna change letters, which is a little bit annoying, but just bear with me if you please. Okay, so first things first. I need a deep breath myself because this stuff can get a little bit confusing. There's something called a polar rectangle. Okay, a polar rectangle is simply if I have two separate r's between two theta values. So in other words, let's let r equal 2 and r equal 4, and we're going to have theta be between, I'm going to keep it simple. I'm going to have theta be between 0 and let's go pi fourths. Okay? So it's the polar rectangle is the region bounded by these values of r and theta. So what would that look like? Well, if we're in the xy plane, I'm going to have a radius of 2, and I'm going to have a radius of 4, and then theta is between 0 and pi fourths. So let me change my color here real quick. I just did that, so I just did it the way I did it so that I could see what was going on. All right, so I could draw my circles easily, really. That's kind of my cheater. All right, that is defined as a polar rectangle, which kind of makes sense. Right? If we let y equal 4 and y equal 10 and let x go between 2 and 4, right? Then it'd be pretty simple if I let a region be bounded by that. Here's 2, here's 4, here's 4, clearly not drawn to scale, here's 10, then my region is this guy. Is this guy. It's this rectangle. Man, I need to take like an art class or something. I am pathetic when it comes to sketching these. Okay, so we have a polar rectangle. Now that's going to be pretty key because I'm going to draw a big one over here and we're going to play with it. Because if you think about it, when we start taking integrals with these things, when I start building integrals out of a base, okay, then what's going to happen is I have to build these rectangles in a very specific way. I have to be able to use a formula. Okay, so I'm still in the xy plane here. We're not even playing with z right now. Here's x, here's y, and I'm going to build a nice, delicious little polar rectangle. Now, a lot of this is straight out of the book, and they'll probably do a better job than I will in terms of describing it, but I want to go over this with you because sometimes reading it out of a book can be a pain in the butt. Now let me change colors real quick. Now what I'm going to do is I'm going to build a grid, and you'll probably be able to see what I'm doing with this grid. All right? I'm going to build this guy and this guy, and then let's go one more just because. Now, what did I just do? I just built the polar equivalent of a checkerboard, didn't I? If this is defined as a polar rectangle and this is defined as a polar rectangle, then this is basically a checkerboard. Now, why do I need a checkerboard?
Well, because I need to make a Riemann sum. If you recall from way back when we first started learning about double integrals over rectangular regions, we built a checkerboard. And each one of these checkerboards is going to have a center of them. And we're going to use those centers for what? Well, what do you think? Well, we're going to use them to define our height when we start building volumes. Because remember, if I want to take or if I want to find the volume of one of these things where I've got f of x, y, I've got some domain, or excuse me, I've got some domain in the xy plane, and I've got an f of xy, and I've got a dA. This is the integral that I use. But now I got to tweak everything. Well, you might already be able to see something, right? Look close. I can already turn f of xy into f of r cos theta, r sine theta. So even if I'm given a function of x and y, I can immediately turn it into r cos theta, r sine theta. Wherever I see an x, stick an r cos theta. Wherever I see a y, stick an r sine theta. This dA guy is where it's going to take us some work. So what did I do? Well, pretty simple to see. These blue lines are changes, are delta r's, right? Right? Oh, wait. I've got blue lines everywhere. Let me be more. Slow down. These blue lines right here that I'm now covering in black represent slight changes in r's. So they're like delta r's, kind of. Right? You with me? That's how I would define that little scraggly guy right there, by delta r. Okay? Now this little guy right here, these guys, these guys could be defined as delta thetas. But I'm going to need to get a little more fancy than that, all right? Because if you recall from back in when we first started doing these double integrals over regions, it was a mess because we had to find these midpoints. So bear with me for a sec. I'm going to find the area of this, God bless it, of this little region right here. So I'm going to bring an r out to it. Right? And if you think about it, if this thing is truly rectangular, then the center of that thing would live in between these two theta values. And it would also live in between these two radial values. All right? So let me write what this means. R sub I star, I promise I'm only going to do this to you guys once, I promise, is going to be 1/2 R sub I minus 1 plus r sub I. In other words, I'm taking the average of the radii as I go out. Theta j star is going to equal the same thing. 1/2 theta j minus 1 plus theta j. Okay? Now, I promise, I'm just going to run you through this really quickly, and then we're spending a lot of days on this. So I'm going to give you the theory, I'm going to give you the equations, and then I'm going to let you do what you got to do, all right? I promise I'm not going to run you through too many examples in this lecture. But I do want to make sure that we understand how this works. All right, first things first. If this right here, let me change the color. If this right here is supposed to represent delta A, well, what is it? It's the difference of two sectors. Let me change that color one more time. So delta A sub I is going to be what? Well, it's the difference of two sectors, right? So it's going to be 1/2 R sub I squared delta theta. That's this guy, delta theta, right? Minus 1/2 r squared, and this is going to be I sub 1. Okay? Now this is going to equal what? Because if I can factor out, look close. Oops, I'm missing my delta theta, aren't I? Go away. I'm missing my delta theta. Stick my delta theta in here. Now here's where it gets fun. I'm going to take 1/2 delta theta, and I'm going to multiply that times ri squared minus ri minus 1 squared. Now your spidey sense may be tingling here a bit, because when I see that, I see a difference of two squares. So I'm going to do something special here. I'm going to go, delta theta is going to sit here. I'm going to go 1/2, and then what I'm going to do is I'm going to take I'm going to factor this. I'm going to turn this into r sub I plus r sub I minus 1 times r sub I minus, that's a times by the way, r sub I minus r sub I minus 1. Now look close. Now you may wonder about this theta here, but just work with me for just a sec, okay? Once I have that, look at what happens. Well, 1/2 r sub I plus r sub I minus 1 is the middle of this delta r. So this actually spits out an r star. That's one of these guys. It's this guy right here. Whoop! That's it. I just stole that. Now, what would this represent? Well, this is my delta r, and this is my delta theta. You see what I'm doing here? So look at what I get for nothing. When I want to find the volume using double integrals over polar regions, I need only go this way. And then what do? I put in f of xy, but we know that turns into r cos theta, r sine theta. Now, I'm totally, look, right now, I should put like a page break in here. I am not going to do the sums as I and j go to m and n, and the limit as n, let's go m comma n, head to infinity. I could do all of that with what we've done here, and this is what gets spit out. I'm assuming that at this point in the game, you guys know what I'm talking about when I start building integrals. So this becomes r, and then what happens to delta r's and delta thetas when I take integrals? This becomes dr d theta. And that's it. That's how it works, which is pretty cool if you think about it. Now, this works when we're dealing with these rectangles. So the question that's begging to be asked is, what's the difference between volume equaling the integral over a domain of f of r cos theta, r sine theta, and then r dr d theta. Don't forget this r. This r is going to drive you crazy because you got r's flying around everywhere. That one always gets stuffed in there. Okay, remember when we did, back when we did integrals with polars in the first place, right? It was 1/2 r squared d theta, and that was like, oh, what do I do with the r? And yeah, that r is going to make you a little bit crazy. So I'm going to change colors here again, and I'm going to say, okay, what happens if it down, it kind of looks black, if down here in my, this is x and this is y, well, now I have, remember how we had, how did we do this one? Like I had that loop, and then I had like a circle, and this guy right here was defined between two polar curves. Let me draw that a little bit bigger. Like, let's say that we had a rose, and then we had a circle. So I'm going to do these in different colors because I'm feeling kind of special. Here's part of my rose, that's one of my petals. And then I had a circle, and I was looking for the area in between these. Remember how this worked? And I had a theta 1 value here, and I had a theta 2 value here that defined where they overlap, or excuse me, where they intersected. However, this guy, and I'm going to avoid r's entirely. I'm going to call them g's. This curve right here would be g of theta, and this curve right here would be h of theta, right? So all that I'm going to do is I'm going to translate this, excuse me, the exact same way that we did in the last section when we talked about double integrals over those regions where it wasn't, we weren't building rectangles basically, we were building them between curves. I'm going to translate it directly. So this guy, instead of just having pretty little rectangles, I'm going to have, let's change colors, let's get back to black. Volume is going to equal the integral over the domain. Now, of the same thing, okay? However, let me pull this guy out. As I've drawn it, what I'm going to have is, on the outside, now look at how it works. I deal with r's first, and then I deal with thetas next. Since I've drawn this, that I go from theta 1 to theta 2, and since I'm going to have a dr d theta, it's going to be the last thing I deal with. Remember, thetas match up, so I'm going from theta 1 to theta 2. And then, what am I going to have in here? Well, I'm going to deal with r's first. So I'm going to have my f of r cos theta, r sine theta, and then r dr d theta. Now the question is, what goes on here? Well, little curve, right? From the little curve up to the big curve. So this is just going to be from g of theta. And this is my notation. It's not the book's notation. People may scream and yell at me like, Ripley, what are you doing? All right, but the way the book writes it is, it says the integral from alpha to beta, that should be an alpha, to beta. So those are basically where I'm going from and to, where the action is taking place. I haven't used that phrase in a long time. And then they write it as, I don't even like the way they write it. They write, how do they write it? Yeah, that's awful. They write it as h1 subscript 1 of theta up to h subscript 2 of theta. And then they write f of r cos theta, r sine theta, and then they go r dr d theta. And then they define, they're saying that alpha and beta are between, I know that theta is going to live between alpha and beta. And then r lives, I guess it's not a bad way to write it, r lives between h1 of theta and h2 of theta. I mean, that's kind of, the reason I got to cheat is because I gave you this delicious little diagram here. So we're back, we're exactly in the same spot we were before. So if I want, oh good gracious, if I let z equal f of x, y equal, let's go xy plus 1. Same thing I was dealing with before, right? xy, let's go xy plus 1. Just one quick example. And I'm trying to define this between, I want this to be interesting, between, but simple at the same time. What do you guys think? Between r equals 4, and so I'm being lazy, bounded by, let's see, I need to be better, above region, bounded by, I'm going to keep it simple, r equals 2 and r equals 4. Okay? All right. Oh, I want it to be a little more interesting than that. Let's go r equals cos theta, r equals sine theta, because that's going to make things crazy. Cos theta, r equals sine theta. Now, if I wanted to, I could graph f of xy equals xy plus 1. This is going to be sine theta. My handwriting is getting worse and worse every year. Oh, by the way, it's my birthday today, just so you guys know when I made this, this video. Okay, so let's figure this thing out. When r, or what do these things look like? So let's go, what do we got here? I know that r equals cos theta looks like this. It's a circle. And I know that r equals sine theta looks like this. It too is a circle. Now, the question is where do they meet? Because I'm going to have to, oh, I want something a little different because this is too easy. I would just have to add those areas, wouldn't I? Well, this is actually this is a decent problem because I know these guys meet at theta equals pi fourths. And I'm starting at 0, right? So, or sorry, for cos, this is going to go from pi fourths back to pi halves. Sine goes from 0 to pi fourths. That's where I'm getting this picked up. I'm moving through this quickly, assuming that you guys remember this from last year. Might be a huge assumption. So in that case, as before, I would label these two guys as area 1 and area 2, right? And then I would just add them up. So let's see what that would look like. All right, what the heck? I'm going to say volume. Now it's going to be a 2-part volume, right? So it would be the integral from 0 to pi fourths, the integral from 0 to, what's that? Let's see, we're defining this first part, sine theta, right? Right, because that's what r is going between, 0 and sine theta. All right. Oh, this was actually pretty. This ended up being a pretty good problem. So this is just going to be r cos theta, r sine theta, plus 1. This is going to be times r dr d theta. Now remember, these guys are just along for the ride. That's the coolest part because we would work the inside first. I'm not going to take you through the full thing. I promise you, all right? But it's not that hard. Then plus the integral from pi fourths to pi halves, because that's going to be the second part, of the integral from 0 to cos theta, because that's where this guy gets built. Again, I'm not putting this in as much detail because we've seen a bunch of these by now, right? Hopefully, of r cos theta, r sine theta, plus 1, and then r dr d theta. And that would give me the overall volume. Now, I promise you guys I wouldn't let this thing go too long with too many examples so we can work on them in class, which is more fun. So I'll terminate the video at this point, and I will see you guys in class tomorrow. Have a wonderful day and get ready for some fun with polar coordinates. All right.